Okay, so welcome to this presentation about the RF breakdown in high power components. Okay, I will basically go through the basics of RF breakdown, and then I will talk about the specific workflows between our dedicated tool for RF breakdown, which is Spark 3D and CST Studio Suite. Basically, I will cover three main workflows: the frequency domain, the eigenmode solver, and the multi-carrier multi-path to analysis workflows. Okay, and then I will just finalize with some summary. Okay, so just as introduction, you know that as time goes by, systems are required to operate at higher and higher power levels. So examples of such applications are satellites to increase the data transmission rate, accelerators to increase the particle energy, and of course high power sources that are serving these applications. As a consequence, of course, we will have an increase of electromagnetic field densities inside the devices. Of course, this will lead to higher temperatures, as Michael just presented in his presentation. But also, and it's not only about temperature, we can also have issues in terms of RF breakdown. Okay, so what do we mean by RF breakdown in this context? It's basically two effects: multiplacting and ionization breakdown, also called corona discharge, gas discharge, and so on. So I will go through these two effects, and Spark 3D is basically taking care of simulating those. So multifactor first takes place in vacuum conditions. So this effect occurs because electrons can be there from any source, like cosmic rays, surface emission from any source. So these electrons are accelerated by the electromagnetic field in the component. Okay, so when these electrons impact on the device walls, secondary electrons are released. If this process is in resonance with the electromagnetic field, or in other words, if the time between electron impacts and the RF field frequency are in resonance, then a discharge can be developed. Okay, this of course degrades the performance of the component. Okay, this is what we can see. This resonance is what we can see here on the right-hand side on this horn antenna, where you can see electrons moving up and down, okay, resonating in the device walls. Okay, so this is regarding multipacting. Regarding corona or ionization breakdown is somehow similar and somehow totally different, okay, because in this case, this can only occur under gas conditions. Again, electrons, which can come from any source, are accelerated by the electromagnetic field within the component. But in this case, what happens is that the high energy electrons impact on the gas molecules, ionizing them. Okay, and then this means that more electrons are generated. Okay, this can eventually lead to an electron avalanche, and then the formation of an electron plasma. Okay, and then the problem again regarding the performance, the degradation of the performance of the component. You can see here in this filter, okay, where you can see how the electron density is growing at a particular power level close to the tuning screw, okay, and that discharge is being developed. Okay, so as said, this effect has several harming consequences. So you have directly an increase of the signal reflection, okay, which also leads to a signal noise increase. On top of that, of course, the discharge is also a very highly nonlinear phenomenon. So it will cause nonlinearities in the system, like harmonics or intermodulation products, again degrading the performance of the component. Even in the case of multipacting, where you can really have electrons bombarding the device walls, can really increase the pressure inside, and then you can eventually result or lead to a gas breakdown. And the gas breakdown is very, very destructive because the temperatures involved are high, are huge. And typically when you have an effect, a corona discharge in a component, for instance, the plating on the surface of the component is totally gone, okay? And you can see really the black spot indicating the discharge. Okay, so the point here is that there are, of course, and from all times, I would say, well-established theories for analyzing RF breakdown, okay, both multipackting and corona. However, such theoretical approaches are based on simplified assumptions, such as simple field distributions because they consider only one dimension, simplified material properties, even they are limited to signal types. So typically only continuous wave signals can be analyzed there. Of course, these simplifications have some consequences. Mainly on one of the typical consequences is that the result that you get with these approaches is the result is very conservative, which means that you are calculating or computing a breakdown power level which is lower than it should be. So you are having, let's say, a kind of over design. But even, which can be worse, it might be that you cannot really do a representative analysis of a particular situation, and this can really jeopardize the whole breakdown analysis. You can maybe state that there is no breakdown at all because conditions are not such that a theoretical approximation can be applied, but indeed other type of breakdown mechanisms are possible. Okay, so again, what is the consequence of using this type of analytical approaches? So the first of, as I said, is component oversizing, so you will be conservative, and typically this means to reduce the field densities and then increasing the component size. Okay, you could also need to perform tests when it is not really needed because you are being conservative in the simulation. Also, because of this lack of representative analysis, it can happen that you have a higher risk of test failure. So you go to the test bench and then you have a failure there. This would delay the design campaign. This would have costs and so on, and delays in the complete design process. And of course, the highest risk, especially if we are talking about satellites, is that you have a failure during operation, okay, which is also something that has happened or happens from time to time. Okay, of course, all this leads to significant time and cost penalty, and of course, we want to avoid that. So, and that is where SPAR3 comes in handy. Okay, so the idea with the SPAR3 is to support engineers in the development of high-power components. The idea is to provide a realistic breakdown analysis, still keeping safety margins. I think this is important to understand that SPAR3 will do a realistic calculation, but when we are talking about high power effects or breakdown effects, there are some, let's say, conditions that can change with the time or that are not fully controlled. And that is why always safety margins are applied, okay? Also, the idea with SPAR3, of course, is that can enable the analysis in complex components versus what you would do with analytical approaches. And of course, the main consequences of all this is that you can increase the reliability of high power components and even avoid very costly high power tests. Okay, so you can speed up the design process, be safer, and of course save time and money. Okay, so that was just the introduction. Now I just want, there are several workflows between SPAR3D and CST Studio Suite. I just want to go today through 3 of them. Okay, basically the general one, which is the most commonly used. One interesting workflow related to narrowband filters, okay, thanks to the eigenmode solver. And finally, the multi-carrier, multi-pack analysis, which we have improved recently thanks to the incorporation of the European standard in the calculation. I will go through that. Okay, so for the frequency domain solver, the workflow is relatively simple. So first, of course, you have to, of course, solve the structure in CST. Okay, and basically the link we have between Spark and CST Studio Suite is through the high frequency finite element solver with tetrahedra, okay? And then of course there you have to define the monitors, the field monitors, you want to use them in Sparse 3D. Okay, typically you need, or well, not typically, mandatorily you need to have an E and H field monitor per frequency you want to use in Spark. Okay, so once you have your design, you can spend any time in doing that within CST, or depending on the complexity of your component and the needs you have. Once you are done, then you can just export these fields to Spark. Okay, and Spark 3D will import those fields through a file, including also the material information. I just want to note here that we have recently added in Sparse 3D a task in the schematic, in the CST schematic. So this way, the export import of the file is not really required anymore. And the Sparse 3D project can be part of the CST project. So the link or the integration is much tighter now. Okay, anyway, once you import that file or you use the Sparse 3D task, you will go through the high power analysis settings. So this will depend on what you want to analyze. In the case of multi-factor, you will need to provide information about the surface properties in terms of electron emission. In the case of corona or gas discharge, you will need to give data about the gas nature, okay, or the pressure range in which you want to perform the analysis. And once this is done, and you set up the settings, which is really pretty easy, I would say, because this is really a dedicated tool for this work. You obtain in an automatic way the breakdown power level, which is indeed, in the end, what the engineer wants, you know, how much power you can handle without developing a discharge in a particular component. Okay, but the tool will not only give to you that automatically, but it also provides some diagnostics. So you can take a look at the discharge location, how the discharge builds up. So you get more information to that can help you to solve the problem once it appears. Okay, just not the number about how much power, about the power level in which you have the threshold of the breakdown, of the RF breakdown. Okay, so this is just the general workflow. And as said in step 1, you need to have your component design in CST, let's say, and then you can export the fields. This is nice, of course, again, this is a very general workflow, but of course it requires to have a representative 3D model. I mean, you really have to have the actual 3D model with the actual dimensions, everything properly set up, optimized, I mean, with the matching you want and so on. So this design process, of course, can be quite a demanding task, not only because of numerical simulations, but also for any requirements you have in terms of electrical performance. So the main drawback here, of course, is that if once you have designed the component after whatever time you have dedicated to that, you don't have enough margin in terms of breakdown, then the only thing you can do is to redesign everything. So you are doing a diagnostic about RF breakdown in the component at the very end of the component design process, okay? So, of course, when possible, it would be very welcome to improve this workflow, or let's say to have a representative analysis, breakdown analysis, not at the end, but to have this representative analysis at the beginning or at the middle of the complete workflow. And this is what we have implemented with the eigenmode solver workflow for narrowband filters. So the objective here is basically to determine the breakdown in a filter, analyzing only one isolated cavity, okay? This can be done thanks to the use or the combination of Sparse 3D, the CST Studio Suite eigenmode solver, and FD3D, the Filter Designer 3D that has been introduced by TNS. So again, the idea is to predict the filter breakdown in a rigorous way without the need to have a 3D match filter. You can imagine that if we are talking about filters, narrowband filters, these are hard to design, okay? And then hard to have a perfect 3D match filter. So again, the idea here is trying to avoid that full design. So how this works? So basically, first, you have your filter specifications, and you can use FD3D, our coupling matrix tool, to extract the matrix for a particular topology. And then FD3D also performs a power analysis in which the stored energy per resonator is given, okay, in the complete frequency band. Okay, so this is something you do before you do any 3D stuff. This is just at circuit level. You know the stored energy per resonator in that particular filter configuration. And that stored energy is the key here because that relates the breakdown field in the isolated cavity with the breakdown field once that cavity is integrated into that particular filter. Okay, so after that, typically what you do is to design the cavity. Okay, this is the typical procedure for filter design. You would design a cavity resonating at the frequency needed with the Q factor that you need and so on. And once you have done that, you can export those fields of this closed isolated cavity to a Spark 3D. And you can do that in the same way as you were exporting the fields with the general workflow. But apart from that, you can also, or you have to provide also the stored energy computed by FD3D. Okay, in this case, I will show a case later on in which you will see that the stored energy is taken for one particular frequency and at one particular resonator. In any case, once you provide the stored energy and the eigenmode fields have been imported, okay, because you have the eigenmode fields coming from the isolated cavity, Spark 3 is able to give to you the breakdown power level once this cavity is integrated into the filter. Okay, and then of course the advantage is that if you don't meet the specifications, you can come back to step 2 and change your cavity. Even you can maybe go to step 1 and change the filter topology because you have a filter topology which results in lower stored energies. Okay, so you have the flexibility to do that before even thinking about the complete filter design, how the coupling will be, and so on and so forth. So this is really giving to you really a nice input before you go through the complete process. And what is important, you are not doing approximations here in terms of field distribution. Of course, the field distribution will not exactly be the same as when using the filter, but it will be very similar. Okay, and then you are really taking the field distribution. You are not doing analytical approximations, and you are getting a quite representative result. And this is what I want to show you in the example. I will introduce now. Okay, so imagine you want to design a narrowband filter with 20 megahertz at 1.755 gigahertz. Okay, so bandwidth is around 0.5% relative bandwidth. Return loss 20 dB, insertion loss less than 1 dB, and this out of band requirement. And we want to do that in coaxial cavity technology. I will go through that. But first of all, you have FD3D, so you can put the specifications there. In this case, we can meet those specifications with a 6-pole filter direct coupled, okay? And FD3D will also give to us, once I select that topology, will give to us also the stored energy, okay? So here I am selecting, you have the 6 resonators. I'm selecting this center frequency, and then the stored energy, the maximum of the stored energy is this value here at cavity number 4. And this will be the number I will use in Spark 3D to convert the eigenmode fields to fields once the cavity is inserted into the filter. Okay, so I'm going to follow now the workflow I explained. So I have to select a resonator shape. I'm selecting this one. Of course, you can do whatever you want, and this is just an example. And then once I have a selection of resonator shape, I can do the design and make the cavity resonate at the frequency I need, okay? And with the needs I have. Okay, so these fields then can be exported to a Spark. I can then put here the stored energy, okay, which was the stored energy of the cavity number 4 at its maximum. And then I compute the breakdown power level, okay. In this case, it's for ionization breakdown, but I compute the breakdown power level as a function of the pressure, okay. And this would be the breakdown power level once this cavity is integrated into the filter. Okay, so now I'm going to design the filter. By the way, I designed the filter. You can see it there. I use FD3D to do this quite automatically, indeed. Okay, so now I have the complete filter design, and I can run my simulation with the general workflow. Okay, and then check what is the breakdown. Again, for the same pressure range, I get this breakdown power level. Okay, for the ionization breakdown, and then I can compare both results. So you see basically that the result from the eigenmode-based calculation and the field and the complete filter analysis difference, the difference is just below 0.5 dB, which is more than enough to go ahead and trust that once you build a complete filter, you will be okay with this workflow. Okay. Okay. Anyway, I would like to make some comments or warnings on that. Of course, this approach is for narrowband filters, but you could extend that to other cases as long as you have a connection between the between the fields in an isolated part of a device. And once that part of the device is in the device itself, an example could be a low-pass filter, okay, with a voltage magnification factor. Of course, the filter field distribution has to be similar to the one of the isolated cavity. This is obvious. Of course, if the breakdown is taking place in the couplings or in the input or output couplings, then of course the breakdown in the cavity is properly computed. But what happens is that you have a breakdown at a lower power level in other part of the component, and then you might have trouble there. But of course, again, this would be a problem you would find once you design the complete filter. And of course, there are, in this case, for instance, I show you have tuning elements, and you have to tune the screws to have the final filter response, and then this can add more, let's say, inaccuracies in this workflow. Okay, but you can see that in this particular case, these changes in the screw length did not have a critical impact on the breakdown power level. Okay. Let me finalize with the workflow related to multi-carrier multi-factor. Okay, so in this case, the workflow is similar to the general one. Of course, in this case, what you need is to have more than one frequency exported. Okay. Of course, this workflow is commonly used in some applications like satellite payloads when you want to transmit all signals through the same antenna, and then you need to combine them before. So there will be parts of, or there will be components in which all the signals are combined. So as said, you do the same as with the general workflow, but at several frequencies, which are, of course, imported into Spark 3D as before. Okay, and the difference here, of course, is that you have to take those frequencies and with those signals, combine them to generate a multi-carrier signal. Okay, you can add here phases and so on, and put the relative phases between the carriers that you have imported. Okay, and once you do that, you do the same. You can calculate the breakdown for that particular multi-carrier signal, and you can perform diagnostics. Of course, there is one point here which is different to the case of single carrier, and which is indeed critical. As said, you can perfectly run this, create your own multi-carrier signal and simulate it with Spark 3D. That's more than fine. The problem is that typically that could not be enough, because you need to somehow identify the worst case phase combination. And of course, you have infinite potential phase combinations. Therefore, we have a problem here, because of course, Spark 3D can analyze anything, but you cannot spend ages analyzing all possible phase combinations. Okay, so this is where the European standard for multi-factor is really helping us. So this standard is from the European Cooperation for Space Standardization. This is endorsed by the European Space Agency. And in this new multi-factor standard, I think it's from 2021 or 2022, there is a method defined there, which is called the envelope sweep approach or the envelope sweep method, which basically takes into account that what matters in terms of a multifactor breakdown with respect to the signal is the signal envelope. Okay, so basically here, with the signal envelope, what we do is to use different widths of that envelope or peak widths, and we optimize phases to obtain those peak widths. Okay, so there is a way to filter out combinations of phases that might not be representative, because in the end will result in the same or similar peak widths, okay, or widths of in which the signal has a high amplitude, okay. And as I said, this simplifies a lot the problem, because this we have implemented this into Spark 3D. Okay, so basically, for instance, here in this case, we have a 7 carrier multi-carrier signal, and we can compute the envelope sweep automatically, obtaining in this case 10 different envelopes. You can see them here plotted, shown. You see that the widths are different for each combinations. And then we can compute for these 10 signals, for these 10 phase combinations, we can compute the breakdown power level. You can see that there are 2 phase combinations that have very high breakdown power levels, but the rest are pretty similar, okay? So this is indicating us that really the breakdown power threshold for this multi-carrier signal will be in that range, okay? So this is really, really useful, because analyzing multi-carrier, multi-factor can be otherwise a kind of nightmare. Okay, so just some summary on what I presented today. So I just did an introduction on Spark 3D. You saw that it is a very dedicated tool for RF breakdown. The main benefit of using it is that you can really increase the component reliability, reducing cost and time to market. And I have gone through different workflows. You see there the list of some other workflows I didn't go through, but I just went through the first 3. Okay, tomorrow there is another, in the other set of presentations, I will also have a talk, and I will go through some of these other workflows, okay? But I hope you enjoyed the presentation, and if you have any question, just let me know.